Hey everyone, welcome back to Everything is Relative with me, Mr. K. Today we're going to be looking at some more Papa Cambridge topical past paper questions on the topic of electric fields again, but this time questions 184 to 188, and this is for Cambridge A-level physics. Now in the last video we did questions that focused mainly on the electric field strength, and in this video the questions focus more on electric potential, so we get a good complete view of electric fields with these past paper questions. Now, as always, I'll leave a link to these questions in the description below. Make sure you are attempting these questions as revision and then using these videos as a guide to help you wherever you get stuck or wherever you feel you need extra guidance. Now, this question, the first question here, I'm starting with question 184. And this is subject code 9702, which is A-level physics. And this is from the summer of 2019, which is May-June 2019. Question paper 4, variant 2, and question number 6 from the paper. And a common starting question when the question is focused on electric potential is to state what is meant by electric potential at a point. Now we should know at least, that the electric potential is the work done per unit charge to bring or in bringing a positive charge from infinity to that point. So it is the work done per unit charge in bringing a, now it's important that you specifically say a positive charge from infinity to that point in question. And so the work done per unit charge bringing a positive charge from infinity to that point in question, and that's electric potential. And so we have to make sure we don't confuse this with potential energy, but potential and potential energy are two different things, and potential is the amount of work done, specifically dividing it by a charge per unit charge in bringing that positive charge from infinity to the point in question. And this we've seen many times. The next question says two parallel metal plates A and B are held a distance d apart in a vacuum, as illustrated in the figure. Plate A is earthed and plate B is at a potential of plus V0. Point P is situated in the center region between the plates at a distance x from plate B, and the potential at point P is V. Now, on the figure below, on figure 6.2, we want to show the variation with x of the potential V for values of x where x ranges from 0 to the complete distance d. So what I'm just going to do is just complete this diagram, and the distance from the top plate to the bottom plate, if I were to move the top plate, if I were to move the plate that's charged V0 towards the 0 volt plate, then that distance would be d minus x. Before I even go to draw a graph of potential against distance for two parallel plates, what I know is that the electric field strength is constant. When I have an electric field set up between two parallel plates, one being positive and the other being negative, then what I have is that the electric field strength is constant, and it is, in this case, it'll be V over d minus x. So whatever the distance, if I move the top plate and I keep the bottom plate fixed, then if I move the top plate closer to the bottom plate, then the value of d minus x will determine the electric field strength, but it'll be constant. And so what it means is, or if I move rather, let's keep the top plate where it is, but if I move from the top plate towards the bottom plate at distance d minus x, then the potential difference V, which is what they told us, the potential difference d will decrease because I'm moving closer to the 0 volt plate, and so it's not going to be V0 everywhere in that region. So as x increases, or as x decreases rather, then the value for, or rather d minus x, as d minus x decreases, then the value of V decreases as well. As point P moves closer to the 0 volt plate, plate A, then the potential difference becomes lower than V naught. But if I look at this equation, and I have that E is delta V by delta X between the region of parallel plates, but E is constant, then the gradient, delta V by delta X is the gradient of the graph of V against X, which is what we have, is a constant value. But it's decreasing from a maximum V naught to 0 volts as we move from plate B to plate A. So if it has a constant gradient, but goes from maximum to 0, what it means is, rather than having, like our typical point charge would have a hyperbola, basically, an inverse relationship with the distance, this will also have an inverse relationship with the distance, but it will be a straight line. And I'll just draw the straight line slightly thicker. You will draw this in pencil. But this straight line means that the gradient is constant. Obviously, all straight lines have a constant gradient. And the gradient of this line at any point will give me the electric field strength, and since the gradient is constant, the electric field strength is constant, which we know is the case between two parallel plates. So be very careful. For parallel plates, the potential difference drops linearly with distance. And so that's how we would get through the first part of the question. Now the question is not over. We are told that two isolated solid metal spheres M and N, each of radius r, are situated in a vacuum. Their centers are a distance d apart, and we have a figure that looks a little complicated, and we are told that each sphere has a charge plus q. Okay, so that's good. Each sphere is identical in size and shape, and they both have the same charge. So there's going to be some symmetry here. Point P lies on the line joining the centers of the two spheres and is a distance y from the center of sphere M. On the figure below, show the variation with distance y of the electric potential at point P for values of y from y equal to 0 to y equal to d. So our horizontal axis, don't be confused here, our horizontal axis is now labeled y. So from 0 to d, we want to show how the potential, the net electric potential, differs. What we must remember is that potential is a scalar. So I'm not adding a vector sum here of potentials, I'm adding a scalar sum of potentials. So what I need to do is understand what the potentials are for each of these spheres. Now each of these spheres are positively charged, so each has a positive potential, which means at no point can my potential be negative. There are no vectors here, there's no direction. It's simply a positive potential plus a positive potential. I should always have a net positive potential. So what I'll know immediately is my graph will always be above the horizontal axis. It's not going to be negative. I'm also told the radius of each of these spheres. From 0 to r is inside the first sphere. From d minus r to d is the radius of the second sphere. Now what I know is that E is 0 inside the sphere. Remember, the electric field strength is 0 everywhere inside a conductor. And electric field strength is equal to minus the potential gradient. So if E is equal to 0, that means the gradient of potential is 0. If a gradient of anything is 0, that means it's a straight horizontal line. So what this means is for inside the conductor, I think I'll just draw this freehand for now. Again, you would be using a ruler if you were drawing this on the graph sheet. You are sketching this rather on the graph sheet. And the potential inside the second sphere will also be constant because the electric field is 0 everywhere inside. And that's from d minus r to d. Now, how do I know what value that will be? Will it be higher, lower? Well, I know it will be positive because it's a positively charged sphere. And I also know it will be the same because sphere A, or rather sphere M and sphere N, are identical. They have the same size and the same charge. And so there'll be some symmetry. And this symmetry will be reflected in the graph. Now I need to complete the potential as I go from the surface of sphere M to point P, to the midpoint rather, and then to the surface of sphere N. Now what I know is that closer to M, M will contribute more to the potential because we are closer to M, and potential drops with distance rapidly. It drops as a hyperbola. So what we get is a total, and remember the potential the total potential at any point is the potential of m plus the potential of n. Both are positive, so the total potential will be positive. And it drops off with distance. And so as we go from m towards n, we get this graph to drop as a hyperbola would. So it's a curve, and the gradient should always be negative. At the central point will be the minimum value of potential. Again, I'm sketching it, so it doesn't really matter where the midpoint is, but it has to be, the midpoint has to be between, has to be symmetrical. And so the other side of the graph would look something like that. And so this graph has a symmetrical shape about the midpoint, which is d over 2. And is that symmetrical? Yes, it is. So your graph would look a lot better than this, but it basically is a basin. So the potential decreases as we move away from m and towards n. We're going into a position where neither of the charges have a great potential. But then as we move very close to sphere n, the potential then increases, because the potential due to n grows stronger and takes over. And the maximum potential at the surface of n is the same as the maximum potential at the surface of m. And that's again because of symmetry and because they have the same charge q. And so this would be the graph of potential against distance from 0 to point D. We have to include the horizontal straight line for inside the spheres. Remember, these are not point charges. And the potential inside a sphere will always be constant. And so this graph I can draw in a very short space of time, but more than likely it's going to be a kind of question where I have to think about what the shape of the graph would be. And also be very wary that potential against distance is not going to look the same as electric field versus distance, specifically because electric field is a vector. And in this case, the vectors would point in different directions. Scalars don't have directions, so positives will always add to positives, and if both were negatively charged, this graph would be flipped around the horizontal axis, and it would be always below the horizontal axis. It will always be negative potential. So just be careful between the difference between electric field strength and electric potential. So a very small graph that we sketched. Obviously yours can look slightly different, but the shape would be the same, and that's worth 4 marks. So make sure you spend some time sketching these graphs, drawing these graphs, understanding what they would look like, and change the scenarios up. Try different scenarios and see what the graphs would look like, or look for questions that give you these different scenarios. The next question is 185, and this question comes from the winter exam of 2019. That's November-December 2019. This is question paper 4, variant 2, and question number 9 from the paper. And guess what? We start with the exact same thing. I'm not even going to type this out again. I'm going to steal this from the previous question. Explain what is meant by electric potential at a point. And you know what electric potential at a point is. It is the work done per unit charge in bringing a positive charge from infinity to that point. Again, you need to know definitions. Part B says, in an alpha particle scattering experiment, an alpha particle or alpha particles are directed toward a thin film of gold, and this is shown basically in the figure. The apparatus is in a vacuum, and the gold 197 nuclei in the film may be considered to be fixed point charges. The alpha particles emitted from the source each have an energy of 4.8 mega electron volts, and we are first asked to calculate the initial kinetic energy in joules of the alpha particle emitted from the source. So the first thing I'm going to do here is, so I don't arrive at some issues later on, is write the mass of a gold nucleus. The mass of a gold nucleus, now I may or may not need this, but I'm going to write it down anyway, is 197 nucleons, neutrons plus protons, times the approximate mass of each one of these, 1.66 times 10 to the minus 27. That's 197 atomic mass units times the mass of an atomic mass unit in kg. And this will be my answer, so give me a value in kg. The mass of an alpha particle is 4, since I have 2 protons and 2 neutrons in an alpha particle. Remember, the alpha particle is a helium nucleus, 2 protons, 2 neutrons, So Z is equal to 2 and A is equal to 4. That's 4 times 1.66 times 10 to the minus 27 kg. And the charge of a gold nucleus, probably going to need this at some point, the charge of a gold nucleus is the number of protons it has, which is 79 times the elementary charge, 1.6 times 10 to the minus 19, and that will give me a value in coulombs. And similarly, the charge of an alpha particle is 2 protons, so 2 times 1.6 times 10 to the minus 19 coulombs. Now, I don't really need that for the first question, but it's good to have that information on hand, at least on the top of my head. I don't need to write it down. Now, I need to take this energy in mega electron volts and convert it to joules. That's why the question is only 1 mark. And so this is 4.8 mega electron volts multiplied by 10 to the power 6. That's a million electron volts for every mega electron volt. I'm getting rid of the mega, and then I'm multiplying this by 1.6 times 10 to the minus 19 joules for every electron volt. So we can see that I will get rid of the megas. I have 2 electron volts on top and 2 at the bottom, so I can get rid of the electron volts, and I'm left with simply joules. And putting this into the calculator, I will get 7.68 times 10 to the minus 13 joules. To 2 significant figures, this is 7.7 times 10 to the minus 13 joules. So each alpha particle will have this amount of energy. And they wanted us to convert it in joules, most likely because we need to use it in the follow-up question. The next question says calculate the distance d of the closest approach of an alpha particle to a nucleus. Now, the distance d of the closest approach, I'm going to assume that all of the initial kinetic energy given to the alpha particle becomes electric potential energy as the alpha particle gets close to the gold nucleus and then stops. So it starts with the initial kinetic energy, all of that kinetic energy vanishes and gets converted to electric potential energy. So what I'm going to do is equate the equation for, or the expression for electric potential energy, 1 over 4 pi epsilon naught, charge of the alpha particle times the charge of the gold nucleus divided by this distance d is equal to the value that we calculated, 7.7 times 10 to the minus 13. And our answer d needs to be in SI units meters, so that's why we calculated the potential energy in SI units. Which means the value for d is 1 over 4 pi epsilon naught q alpha QAU divided by 7.7 times 10 to the minus 13. Now, I always like to rearrange the equation and do the algebra first, but again, how you go about solving the problem is up to you. So remember, 1 over 4 pi epsilon naught, we said before, was 8.99 times 10 to the 9. Saves time from having to write 1 divided by 4 pi times 8.85 times 10 to the minus 12. We can remember the entire fraction because it's a constant. And we multiply this by 2 times 79 times the elementary charge, 1.6 times 10 to the minus 19. Be careful, we have to square that because we're multiplying it through twice, divided by 7.7 times 10 to the minus 13. And if we put all of this into a calculator, we get 4.722 times 10 to the minus 14 meters. A very small distance, as we'd expect. So 4.7 times 10 to the minus 14 meters. And essentially what is happening here is, since the alpha particle cannot get into the gold nucleus, there comes a point where the alpha particle is sort of at the edge of the gold nucleus. And so the distance d between the center of the alpha particle, or rather the center of the gold nucleus and the alpha particle, since we assume the alpha particle is very small, that distance is d. And so what I'm essentially getting is the radius of the gold nucleus. The gold nucleus being much bigger than the alpha particle. So the alpha particle can even be considered to be a point. And so the next question says, use your answer in B2 to comment on the possible diameter of the gold nucleus. So the diameter will be 2D, roughly. And that's a possibility. So that would be on the order of, well, 9.4 times 10 to the minus 14 meters. So probably 9.4, or rather 1 times 10 to the minus 13 meters on order of magnitude. So what we can say is that the diameter to be concise, we can say it must be less than 10 to the minus 13 meters. Note that we can't get an accurate feed for how big the nucleus is, but we at least know that it has to be less than 10 to the minus 13 meters. And so anything smaller than that will be like our value calculated. So if the alpha particle gets all the way right to the edge of the gold nucleus and touches the gold nucleus on the outside and then gets pushed away, we at least know the diameter must be less than 10 to the minus 13 meters. So that's as much as we can conclude from that kind of problem. So an interesting problem, tests our knowledge of particle physics as well. The next question is question 186, and this comes from the March exam of 2018, and this is question paper 4, variant 2, and this is question 7 from that paper. And guess what the first question is? It's going to be a common first question. It's going to be something that we're going to see often. But it says, state what is meant by the electric potential at a point. Again, is the work done per unit charge in bringing a positive charge from infinity specifically to that point. Next, another familiar type of question. The centers of two charged metal spheres A and B are separated by a distance of 44 centimeters, as shown in the figure. A movable point P lies on the line joining the centers of the two spheres, and point P is a distance x from the center of sphere A. The variation with distance x of the electric potential at point P is shown. Again, we've never seen a graph of potential against distance anywhere in our notes or in our textbooks for two charges. We've only ever seen it for one. So this is the graph of the net potential. If I were to add the two potentials and draw a graph at every point, this is what I would get. And I somehow need to use this information to determine things about those two charges. And so the first thing I need to determine is, using the figure, I have to state and explain whether the two spheres have charges of the same or opposite sign. Now, if I think about the previous question, if I look at this, the potential is always positive. It never cuts the horizontal axis. It never goes to a negative value. That means that if the sum of the potential at A and the sum of the potential at B is always positive, even when I get close to the smaller value, which looks like it's closer to point B. This means that both of the charges, both of the spheres must be positive, okay, because the potential is always positive. So I can write it just as that. Since I know that this is a vector sum, or a scalar sum rather, I can simply say that the potential is always positive. So the spheres must have the same sign. Or you can say specifically that the spheres must both be positively charged. So the spheres must have the same sign. The potential is always positive. Okay. Next, we are told that a positively charged particle is at rest on the surface of sphere A. The particle moves freely from the surface of sphere A to the surface of sphere B. And we want to describe qualitatively the variation, if any, with the distance of the speed of the particle as it moves through these points. So a very wordy question. How does the speed of the particle vary with the distance? So we want to know if the speed varies, and then how it varies. So I take a positively charged particle, and it could be any point particle, and obviously will get pushed away from A, and as it approaches B, it's going to start getting a stronger force by B, which is going to push it back. And so this particle is going to move from A towards B and then possibly back towards A again. We want to know how it's going to move. Well, the diagram alone might make it a bit difficult, but the graph might help us determine how the speed is going to change. So what I first need to do is I need to remember that the charge of this charged particle Q times the potential at any point is going to be equal to the kinetic energy it's going to gain. And also this value of QV is the work that's being done on the particle to push it between A and B. And work is force times distance. Force being ma times the position of the particle x. So what I can see is that there is a relationship between the potential and the acceleration. If I have a high potential, I have a greater force on the particle and have a greater acceleration. Why am I bringing the acceleration into this? Because the acceleration tells us how speed varies. They didn't ask us for the speed, they asked us for the variation with the speed. So we need to know what the acceleration is at any point. And so if I look at the way that the potential is varying, I can tell how the acceleration is varying, and hence the speed. And so the first thing I'm looking for is from 12 to 25 centimeters. So 12 to 25 centimeters is the steep descent of the graph. So I'll draw an x there, and then an x there. So 12 to 25 is the steep descent of the graph. Now what we can see is that the potential is decreasing in that way. So it's decreasing, but it's always positive. So the acceleration is always positive. The particle always accelerates, but you can see that the rate at which the potential is decreasing is also decreasing. And so the acceleration is decreasing. So what this means is that because the potential is positive, the particle is accelerating. Acceleration means its speed is increasing. But it's becoming less and less steep, which means the acceleration is being less and less steep. And what does that mean? The acceleration is decreasing. So the speed increases, but at a decreasing rate. So be very careful. The rate at which the speed is increasing is decreasing. Or you can say the speed increases, but the acceleration decreases. That's exactly the same thing. The rate of change of speed is acceleration. So the speed is increasing, but the acceleration decreases. So the force is getting less and less as it's getting further away from A. Still accelerating, but doing so at a lower rate. And what happens as it passes through x is equal to 26 centimeters? So at x is equal to 26 centimeters, we have our turning point of our graph. That's the minimum value for v. So that's the lowest amount of work that will be given to this particle. And so what happens is the acceleration also has the lowest value, and the graph is not changing. So there's a flat spot for an instant in time at 26 centimeters, which means the speed is now maximum. So there comes a point where the acceleration stops decreasing, reaches zero for a very brief time, and then the speed is a maximum. You can actually think of this potential versus distance graph as a little valley, and the positive particle, as a marble. If I throw the marble into this little valley, it'll accelerate down towards the center, but it will do so slower. It'll accelerate with a lower and lower magnitude because the gradient of the slope is decreasing. There will be no acceleration at the bottom point, so the speed will be a maximum, and then move up the other side like the marble would do, move up the other side, and obviously you can imagine what's going to happen as it moves up the other side. So as we move from 27 to 31 centimeters, that's the upward, the incline, what happens to the marble? It obviously starts to decelerate as it moves up the incline. And so the particle will actually decrease. The speed, rather, of the particle decreases. And can we state how the speed decreases? Saying that it decreases is not enough, but it decreases, And the gradient gets steeper and steeper and steeper till we get to the top of the right-hand side. So it decreases at an increasing rate, or the deceleration increases, or the opposite, the negative acceleration increases, the acceleration pointing in the opposite direction. The speed decreases very rapidly as it moves up the other side because the gradient increases. So the speed decreases at an increasing rate. When it reaches 32 centimeters, when it reaches the point where I've marked as an X, at 32 centimeters, what's happening? Well, the speed is still decreasing. After 32 centimeters, well, we know that it's reached the surface, so it's not really going to go into the second sphere. But when it reaches the surface of the second sphere, its speed is still decreasing. And we don't have any further time or any further knowledge of what happens afterwards. But it obviously would be shot to the left after this time has passed. So I can simply say that when it reaches 32 centimeters, the speed is still decreasing. So you can see that these kinds of questions, we did this kind of question for electric field strength against distance, and now we're doing it for potential against distance. So this is why I say always make sure you go through graphs like these and seek out as many graph type problems as you can, because they can be quite conceptually difficult to understand. So that was a fairly long question. If I had to unravel everything for the first time, it would take a significant amount of time, and hence the 4 marks were kind of justified. Next, we are told that the particle has a charge of 3.2 times 10 to the minus 19 coulombs and a mass of 6.6 times 10 to the minus 27 kgs, and we are asked to calculate the maximum speed of the particle. So how do I go about solving this problem? Well, what I remember is that the potential energy gained by the particle will be converted to kinetic energy as it moves. So QV is a half mv squared, where the V on the left-hand side is a big V for potential, and the V on the right-hand side, the speed of the particle. So how do I know which would be the maximum speed of the particle? Well, it will be the difference, the biggest difference in potential that will allow for the biggest speed difference. And we can see, again, if I drop the marble down the slope, then the biggest speed biggest speed will be at the bottom, and it will be for the speed it gained when it was released from the top. And so what I need is the potential difference, or the difference in potential between the highest point and the lowest point on the graph. That's going to be the point which the particle is going to be accelerated for the longest amount of time and reach the highest final maximum speed. And so I rearrange this equation to solve for the speed, and I get little v is the square root of 2q times big V divided by m, which is the square root of 2 times the charge of the particle, which is given as 3.2 times 10 to the minus 19 coulombs, multiplied by the potential difference, which I get from the graph as 2.14 at the highest point, and the lowest point I get 1.43, which you can double check and do so accurately with your pencil and ruler. So that's 2.14 minus 1.43. Am I happy? Not quite, because I must remember that my units here are 10 to the power 4 volts. So there's a prefix in front of the volts. Make sure to write that down. And all of this divided by the mass of the particle, which is given 6.6 times 10 to the minus 27 kg. And what I get is the speed of this particle is 8.30 times 10 to the power 5 meters per second. Or to two significant figures, 8.3 times 10 to the 5 meters per second. And so when answering a question like that, always make sure to look for the potential difference between the highest and the lowest potential, and that will result in the maximum speed of the particle anywhere between two spheres of charge. The next question is question number 187, and this is from the winter 2018 exam. So W18, question paper 4, variant 1, and this is question number 6 from that exam paper. And I'm not going to tell you what the first question is. Define electric potential at a point. And so as I've been doing all this time, I'm going to copy and paste that definition. So state what is meant by, or define what is meant by, the electric potential at a point. It is the work done per unit charge in bringing a positive charge from infinity to that point in question. Now the next question is different. They say, state the relationship between the electric potential and the electric field strength at a point. Now, you may have seen this mathematically, or you may have seen it in words. Since we don't do calculus, we simply write it as the electric field strength is minus delta V by delta R. So in words, how we would write this is we would say that the field strength, E, I need to write that mathematical equation in words. The field strength at a point is the negative, I have to write the word negative to include the minus sign, or is the minus the potential. Now when we take the difference in something divided by the difference in position, we call that the gradient of that something. So it's negative of the potential gradient at that point. So delta V by delta R, if you like calculus, dV dr. So the field strength at a point is the negative of the potential gradient at that point. And so if I have a graph of V against R, and I find the gradient of that graph at any point, guess what I get? I get the electric field strength at that point. So it's good. I can go from one graph to the other very quickly if I need information of one quantity that I'm not sure of. Next, we are told that two parallel plates, A and B, situated at a distance of 1.2 centimeters apart in vacuum, as shown in the figure. And we are told that plate A is earthed and plate B is at a potential of negative 75 volts. And we have a helium nucleus situated between the plates, a distance x from plate A. Initially, the helium nucleus is at rest on plate A where x is equal to 0. Now, the helium nucleus is free to move between the plates, and by considering energy changes of the helium nucleus, we want to explain why the speed at which it reaches plate B is independent of the separation of the plates. Well, what I know here, I wonder why is the speed at which it reaches plate B independent of the separation? So irrespective of how far away the plates are, it will always reach plate B with the same speed. So now the gain in kinetic energy as the particle moves from plate A to B is obviously equal to the loss in potential energy. So the potential energy will push the charge away towards the negative plate, or it will be pulled towards the negative plate, either way. And so the speed is independent of the separation. But I haven't actually said how, so I've left this part for last. The speed is independent of the separation because I need to write this equation down. I have to write it down to explain why there's independence. And that's because the gain in kinetic energy is a half mv squared. And this is equal to the loss in potential energy, QV. So we don't have the distance between the plates, 1.2 centimeters anywhere in here. We don't have the distance x in this equation. So I can have the plates as far apart or as close together as possible. What does matter is the potential on one of the plates, which essentially depends on the charge and not the separation between plates. And so the speed will always be the same. V will always be the same because the mass of the particle and its charge are not changing either. So I must specifically state the mathematical equation and must say that the gain in kinetic energy is equal to the loss in potential energy. And writing that equation down, the speed is independent of the separation. So that's why the speed will not be determined by how far away the plates are. Now the next question says, as the helium nucleus, they tell us that the mass number is 4, atomic number is 2, moves from plate A towards plate B, its distance x from plate A increases, and they want us to calculate the speed of the nucleus after it has moved a distance 0.4 centimeters from plate A. What we remember from one of our previous questions is that as we go further away from plate A, the potential difference, or even as we go away from plate B towards the plate A, the potential difference in magnitude drops from 75. So it'll drop from minus 75 to minus 50 to minus 25 to 0 at some point. And so when I am a distance x from plate A, that is not the full 1.2 centimeters, I have a magnitude of a potential difference which is less than 75 volts. But how am I going to figure that out? Well, what I know is that the potential changes linearly. So if I'm going a distance of 0.4 away, over a total distance of 1.2, I'm going a third of the way across. And if the potential is decreasing linearly, then I want a third of the value of 75 volts. And so what I get is that V, so 0.4 over 1.2 is whatever the potential difference or the potential at that position x is over 75. And so I get this to be 0.4 over 1.2 multiplied by negative 75. And guess what? I get this to be minus 25 volts. And so now I can use this information to calculate the speed of the nucleus after it's moved this distance, because it's not doing the full 75 volts of work. It's Q times V is equal to a half mv squared, which means that the speed little v is the square root of 2qv over m. And so I'm going to write this as the square root. Now I can ignore the minus sign since I'm only calculating the work done. The minus sign doesn't really matter here. The charge is the charge of this alpha, or this helium nucleus rather. 2 protons, which is 2 times 1.6 times 10 to the minus 19, multiplied by the potential difference, 25 volts. And then I divide this by the mass. Now be careful, the mass is 4 nucleons times 1.66 times 10 to the minus 27 kg. Everything considered, I should get this to be 4.909 times 10 to the power 4 meters per second. To two significant figures, the speed is 4.9 times 10 to the 4 meters per second. Now again, just be very wary that the potential difference between the plates may be 75 volts, but that's only where the separation is 1.2 centimeters. So even though the electric field strength is constant everywhere in between the plates, if I move closer to one of the plates, if I move away from one of the plates and closer to the other, the potential difference is going to drop. The magnitude of the potential difference will get smaller until it reaches the second plate, and in that case, the potential difference will be 0. And so this is a 9-mark question, also relatively interesting, and took a bit of time because we had to understand conceptually what is happening when we are solving this problem. But once you get the hang of it, it generally doesn't take that long. The next question, and this is the last question for this video, is 188. And this comes from the winter exam of 2018. This is question paper 4, variant 2, and it's question number 6 from that exam. And the first question, as always, since these questions are all based on electric potential, is to define the electric potential at a point, which we've done too many times now, but we can't put a price on how important it is to know these definitions. State what is meant by the electric potential at a point. It is the work done per unit charge in bringing a positive charge from infinity to that point. And the next question is one that we saw as well. What is the relationship between the electric potential at a point and the electric field strength at that point? Well, we've seen this in the previous question. The relationship is that E is minus delta V by delta R. The electric field strength is minus, or is the negative of the potential gradient at that point. So specifically at a point. The field strength at a point is minus the potential gradient at the point. Take the graph of potential versus distance, find the gradient, put a minus sign in front of the gradient, and there you have the field strength. That's the very specific point. We're then told that two similar solid metal spheres, A and B, each of radius r, are situated in a vacuum such that the separation of the centers is d. So They are identical in shape and size. The charge plus Q on sphere A is much larger than the charge plus Q on sphere B. So both charges are positively charged, but A has a much greater magnitude of charge than B. And the movable point P is located on the line joining the centers of the two spheres. And the point P is a distance x from the center of sphere A. We are told on figure 6.2 to sketch a graph to show the variation with x of the electric potential between the centers of the two spheres. Aha! So similar to the sketch we did before, two positively charged spheres, they have the same shape and same size, but they don't have the same charge. So the radius of sphere A and the radius of sphere B, we can see they both take up one big block in this figure. But the graph is not going to be completely symmetrical. So what I need to do is first sketch the potential inside sphere A. Remember what we said about the potential inside a sphere? It's a constant value. And it's always going to be positive because the sphere is positively charged. In fact, the potential everywhere is going to be positive because both spheres are positively charged. So a positive number plus a positive number will always be a positive number. It's not going to touch zero anywhere. And the potential inside sphere B is going to be a lot less. And so what I will do is draw the potential for sphere B anywhere lower than it is for sphere A. Again, we are sketching. We aren't drawing a graph, so I don't have actual values. Now I know that the potential will decrease with the distance as it moves away from sphere A, but sphere A has a lot more force than or greater potential rather, as we go further away from it because it holds a greater charge. And the influence of sphere B only becomes apparent when we get closer to sphere B. So the minimum point will no longer be in the center because sphere B has a much lower charge and hence a lot less potential, a lot weaker field strength. And so what I have is a point that is where the minimum exists that is closer to B and further from A. But what I will have is the potential drops as a curve, a concave curve. This is going to be very difficult. Again, easier if you're drawing it with pencil, but still not the easiest thing to draw. I need to draw a curve where the gradient is always negative up until my central point and to my point where the potential is minimum. And then from that point onwards, the potential of sphere B takes over and the total potential grows as we get closer to the surface of sphere B. And so this is a very, very poorly drawn diagram. But as you can see, this graph is curved as we go from the surface of sphere A. It decreases to the point at which it's a minimum, which is closer to sphere B, closer to the surface of sphere B, and then increases as we get to the surface of sphere B. Inside A and inside B, we have that the potential is constant because the electric field strength is 0, and the electric field strength is related to the gradient of the potential versus distance graph. And so if that's the case, gradient equal to 0 means straight horizontal line. And so you would have to draw this slightly better than I have, but you can see that this is a curve. It's not a straight line in between the two surfaces of the sphere. Now that question is worth 4 marks, so it's very important that every section of the graph is neat. Mine is not totally neat, but again, it would be much easier drawing it in pencil. Draw it freehand and make sure that your horizontal lines look horizontal and your curves look like curves. Basically, shouldn't be a straight line. But what would happen? How would I don't have a question like this on hand, but what would happen as a matter of interest if the big charge were positive and the little charge, small letter q, was negative? I'm just going to sketch a graph to show what this would look like, even though this is not in the question. This is just out of curiosity. So I draw the potential on the y-axis. I draw positive and negative potentials. And then I draw the position on the x-axis. Now what I know is that closer to the negative charge, the potential will be constant and it will be constantly negative because the smaller charge would be negative. And the magnitude for the positive charge would be bigger. So inside the positive charge, we'd have a bigger potential. And I would still have the same shape, but at some point the potential will be equal to 0, and that potential will be equal to 0 closer to the small charge. So I have a curve just like I did for the graph above, but at this point v is equal to 0. The potential of a smaller sphere begins to take control as we get closer to the smaller sphere. And the curve will have the same shape, but now in the negative direction. And so what happens is the negative portion, or the portion closer to the negative charge, will be flipped about the horizontal axis. Still symmetrical, but now flipped about the horizontal axis. So there will be a point where potential is 0. At some point, a plus and minus must give us 0. And then I still have this sort of hyperbolic shape, but now inverted and in the negative portion of the graph. And so if one of the charges were positive and the other were negative, this is how they would look. You can see the left-hand side is still bigger than the right-hand side. And so when answering questions like these, always make certain that you understand, do I know what my charges are? Am I drawing or plotting or sketching a graph of field against distance or potential against distance? So I hope these questions were helpful. We moved on from field strength in the last video to electric potential in this video. I hope this covers the topic of electric fields totally and enough that makes you feel confident for the exams. But again, there are hundreds of questions out there that you can work on and apply these skills on to see that you've really understood. If this video was helpful, please leave a like, comment down below, subscribe to the channel if you're not subscribed. Let me know if there's anything that you'd like me to cover or if there's any improvements I can make. But for now, that's all from me, Mr. K. I'll see you again next time on Everything is Relative.